We are very happy today to have Julian Sonner from University of Geneva and on sabbatical at Harvard. He will tell us about chaos and stochasticity in quantum gravity. Please.
All right, so thank you for having me here. It's truly a pleasure to be here. As some of you know, I used to come here quite a lot around the time when I was a graduate student. And it's certainly great also to see this wonderful new building. So yeah, it's always a pleasure to be here. So now, given recent events, I thought I should make at least one disclaimer. Probably at the top of your mind is whether the speaker will make lots of gratuitous and silly jokes about the Holy Father, to which the answer is, although there's one typo. No, so this will be the last one. Okay, so to go to the actual talk. So let me start with a very broad introduction. So I was informed that this is a seminar which is actually somewhat broader. So I'm afraid that if you're experts on the subject, I'm not going to tell you anything that you don't know about, but maybe I'm still going to be able to amuse you somewhat. Well, as you know, black holes are objects that were long time thought to be in the realm of speculation. But of course, recently in particular, although this goes back to the 70s already, it's clear that black holes are also more and more subject to actual experimentation, and of course, the classical aspects of black holes. And one way of bringing that close in a visual way is that, for example, we can see black holes, as here in this picture of the Event Horizon collaboration of a supermassive black hole that is actually in the center of our own galaxy. But despite the fact that they are sort of under control, or let's say available to do experiments with, we still don't really understand them very well in a theoretical way. So these black holes are extremely simple classical gravitational objects, but arguably still the most puzzling objects that we know about that exist in our universe. And one of the paths one takes to argue for this is that at the semiclassical level, these objects look as if they were thermodynamic objects. They certainly have partition functions that behave like thermodynamic potentials. They have an entropy, for example, the famous Bekenstein-Hawking entropy, which is proportional to the area, and with all these constants of various branches of theoretical physics united in front of it. And for example, also associated with this thermodynamic behavior, they have a temperature, which is also the famous Hawking temperature, which I'm writing here just for the simplest example of a Schwarzschild black hole. And a question that has occupied theorists for a long time is, what do we make of this thermodynamic behavior? How do we make sense of it? Of course, loads of progress has been made on this, in particular in the context of string theory. So the more detailed question that this suggests is that we have some macroscopic object which shows thermodynamic behavior, and what we'd like to understand is how do we make sense of this macroscopic thermodynamic behavior in terms of a microscopic, for example, Hilbert space type description in terms of a number of microstates whose aggregate behavior on average gives rise to this black hole entropy. So for example, one might want to understand the macroscopic entropy as a microscopic state counting where this macroscopic entropy is given as a logarithm of a number of microstates. And as many of you are well aware, there have been successes, in particular in the context of string theory, to realize this. For example, the Strominger-Raffer count of certain supersymmetric black holes, where they identified microstates to count. But that's, of course, old news in some sense. So what I would like to talk about today, or what underlies the subject I want to talk about today, is a somewhat more detailed question, which I summarize here as what is the microstructure of these black hole microstates that I'm just kind of sketching here. And in particular, what I mean is, not only the question of how many are there, but also how are they arranged, and how are they arranged in such a way that we can understand, for example, dynamical questions about. And by thinking about this, also can we learn something about the microstructure of what I call H gravity here, sort of the gravitational representation of what's going on there. Now, the physical principle that I want to mostly rely upon is to think about black holes as chaotic systems. So in many contexts in physics, we have this connection between thermalization and chaotic dynamics. So the thermal states are very simple. They are specified by only a few parameters, for example, their temperature, their pressure, their entropy, you've seen them, a few other microscopic variables that these thermodynamic potentials can depend upon. But at the same time, we also know that the underlying microscopics can be extremely complicated. And in fact, in theories that thermalize, we typically say that the underlying microscopics is a very complicated chaotic dynamics. And chaotic dynamics here has the effect to be a randomizer in the sense that they drive the system into a simple state that can be understood statistically in a random sense, driving to very emergent simplicity. So one example that we are all familiar with is if you take a cup of coffee or a cup of tea and you put in some milk, then you have some very complicated swirls of, for example, turbulent or convective dynamics. But eventually you will come to a state in which the milk and the surrounding coffee, for example, are at perfect equilibrium at the same temperature in a stationary configuration, which is much simpler than the state that we started with. And of course, to get from here to there, we witness some very chaotic dynamics. And so gravity behaves in much the same way. One can ask more quantitatively, it's not something I'm going to talk about much today, but how effective a randomizer is chaos in a quantitative sense. But for example, something that visualizes this kind of chaos for gravity is something, again, this is just as a motivator. This is not going to be directly related to what I'm going to talk about technically in this talk today, but I still think I wanted to show it to you. So this is from some older work with these collaborators where we actually looked at the fluid description of a black hole, semiclassical black hole. And we gave initial conditions which corresponded to counterflow. So you can think of this as some membrane that has a fluid on it. And you can give some initial conditions that have an unstable, turbulent mode. And by driving it, we were able to show that this black hole actually leads to steady state turbulence. And Ben even made a movie of that. And you will see in a second why I wanted to show you that movie. So basically, this is a two-dimensional slice of the black hole horizon. And you see that you get this eddy flow. Of course, he chose the colors such to be related to tea in a cup. He's very British. He wouldn't think about coffee. But you find exactly this turbulent inverse cascade that you would expect from a turbulent two-dimensional system. And we even made contact with Kolmogorov scaling laws here, which you get in the steady state. Now, there are, of course, many other ways in which black holes are chaotic. So I will spend a couple of minutes reviewing that. So basically, the point is that we often look for a principle of formalism that serves as a guiding light in the possible theories of quantum gravity. And in recent years, I think we've seen quite a lot of progress in this context where we use quantum chaotic principles or insights of quantum chaos to think about it. So for example, some highlights of this is that, if you think about the black hole horizon, you can actually link this to a sort of idea of chaos that is very similar to the idea of Lyapunov of unstable phase-space trajectories. The idea of looking at the spectrum of the system energy spectrum, the spectrum of the Hamiltonian, that actually turns out to be encoded in space-time topology. This topic here will be much closer related to what I will talk about. And also something that I had no technical, I was trying to get rid of this cursor, but I guess it's not my cursor.
Yeah, so.
Is something that in recent years also, I think, starting to be very interesting is the relation between von Neumann algebras and space-time emergence, which also may or may not in an interesting way be linked to this ergodic hierarchy. I think that's a very interesting.
What is ergodic hierarchy?
Well, as I said, I don't work on it. I don't plan to spend a lot of time on it. But basically, in classical dynamics, in classical chaotic systems, there exists a classification of different, let's say, necessary conditions for a system to thermalize, and they form a sort of ergodic hierarchy, if you want. But as
you're making an analogy between that and the types of von Neumann algebras.
People want to understand certain aspects, but I really this is not my talk here. I don't want to get into it. But for example, Nima, who is in the audience, would be very happy to tell you about it more. Yeah, no, honestly, this is just an overview where I think that chaos has recently been very useful. And so this I just put there because I personally think it's interesting, but I don't want to talk about it. I also don't have the expertise to give a whole talk on it. Anyway, so now here is some more background on chaos and quantum ergodicity. So we've now harped on about this topic that black holes are thermal states. And so one interesting thing would be to actually understand how they arise as a process of thermalization. So in classical mechanics, this would be most effectively done by thinking about phase space of the system, to think about something like chaos in the Lyapunov sense, to which you might add property of mixing, and you end up in an ergodic state where basically time averages of the system reproduce averages with respect to the thermal ensembles. But that's not where we are. We are in a quantum world. And in a quantum world, thermalization is actually related to what on the surface looks like different concepts, namely this idea of eigenstate thermalization, ETH, and random matrix theory, RMT. And normally, people usually people link them to different timescales in the process of the thermalizing dynamics of the system. And these different timescales have corresponded to the kind of gravitational signatures that I already mentioned, that I will say again on the next slide. So a system that starts out far from equilibrium and that will approach some equilibrium thermal state as a function of time will well, the first interesting timescale that I want to mention, there is one previously, which is just a local thermalization timescale, which is like order of the inverse temperature. But the first interesting timescale that has shown up recently in these gravitational setups is what people call the scrambling timescale, which is a timescale on which information gets delocalized on phase space, and which is linked also to the Lyapunov divergence of let's say, nearby trajectories. It's really diagnosed by a 4-point function in a quantum system, but let's not go into it too much. It's a timescale that's typically logarithmic with the number of degrees of freedom. Now, the timescale that's associated to this RMT and ETH type physics is typically called the Thouless timescale, and that's a timescale which we have determined in certain holographic systems to go polynomial in S, so it's much, much later. And it is a timescale where you can start thinking of the system as behaving as if it were governed by a random matrix Hamiltonian. And then the latest timescale that one might cite here, which is of relevance, is what people call the Heisenberg timescale. It's a timescale that is so late, exponential in the number of degrees of freedom, that physics becomes sensitive to the level spacing between individual microstates. And that level spacing is typically denoted as delta, the average level spacing, so the timescale is 1 over delta.
So,
yeah.
Here, when you say quantum mechanics, you have some sort of a matrix quantum mechanics in mind of the, because if the system has a very sharp sense of locality, that log S is not really scrambling time.
No, I would say because you have like, yeah, in what sense would you say the scrambling time?
Like in,
I mean, you have also the local spreading. You're talking about this spreading with respect to the butterfly velocity.
say, yes.
Yeah, sure. But here, let's not think about those light cones. It's just here a general idea of what these timescales are, and typically I would call this the scrambling time.
Sure.
There was another question. Yeah.
Is Poincaré recurrence time ever relevant? That's e to the s, right?
Probably yes. Which would of course be much later. I don't have anything interesting to say about Poincaré recurrence time today, but yes, you could have also put that time scale somewhere here. I mean, there are other papers that argue about this. Notably, there's a paper by Barbon and Rabinovich who talk about this, but so far I haven't seen much more, let's say, technical development on talking about Poincaré recurrences in gravity. But in principle, of course, would be nice to understand it. Yeah.
I'm sorry, I'm actually confused about Nima's question because I thought that this scrambling time, if you define it as the time it takes for the initial local perturbation to basically spread over the entire system, then if you're in typical local systems, then it cannot be given by this type of scaling. Like this type of scaling typically happens for the large N theories where you have the gravity dual.
Oh, sure. So first of all, it is true that this is only this here. I'm only thinking about a system which has some separation scale like large N, for sure.
Yeah, I see.
Yeah, so it's like matrices.
Okay, so to wrap this up, so this has been linked to various characteristic scales of, let's say, gravity of black holes. So for example, the local thermalization scale, which I even skipped, this we should think of as the formation time of a black hole. So you start with an initial state that will collapse to form a black hole. The time scale to see the emergence of, say, a apparent horizon, that should be this local thermalization scale. The scrambling should be or has been related to shockwave scattering, and basically has to do with like the blue shift effect of the black hole horizon. And this taueless time, and even to some extent the Heisenberg time, is this topic that has been linked to space-time wormholes. So the space-time wormholes are linked to this Heisenberg time, which also some people call the quantum ergodic time. That is what I mean by wormholes and ergodicity. Now, that's, I think, has been really very nice work. Like we have sort of found, let's say, universal signatures of quantum chaos within, let's say, universal things that happen to black holes, and maybe gravity more general. But actually today, what I want to say is that I want to be a little bit more ambitious in some sense. I would like to take really this chaos, as I will describe, as the foundational principle to build a theory of gravity. And what is surprising, at least in low dimensions, is that in fact, it seems like we can build a model that works on all these timescales. It's not like we take a timescale and we pick out some signature of chaos and we identify. We actually build a theory that works at almost all timescales. And this almost I put in there because it's not so clear whether we can really do things at the Heisenberg scale. And so the question about the Poincaré recurrences is then even more relevant. I don't know if we can go that late. But okay, so, and it's based on work with a number of collaborators. So in particular, Dan Jeffries, Polchmeyer, Bar Mohamed Sanov, and also Alex Belin, Jan de Boer, Dan Jeffries, and Pranjal Ram. Second part, in fact, will be based on a paper with Pelliconi and Valinde, but I will say so when I get there. So now let me get into the way we get at some sort of random matrix type description that we want to capitalize on from the point of view of first chaos and then from the point of view of gravity. So the thing that we often call matrix models, it's also alternatively called random matrix theory or RMT. And what we're really all talking about is matrix integrals, meaning integrals that are defined over matrix valued degrees of freedom. So going back to work by Wigner and Dyson, the way that this is related to quantum chaos is as follows. So what they suggested was that if you take a quantum system which has some Hamiltonian H, which satisfies the properties that it's somehow a quantum system which is intrinsically chaotic, the way of saying that is to say that as far as the levels are, the energy levels are concerned, we can replace the actual Hamiltonian of the system, the actual physical Hamiltonian of the system, with instead a probability distribution which has a judiciously chosen potential and symmetries and average over all Hamiltonians that come from this probability distribution. And that is the random matrix theory in the sense of Wigner and Dyson. So one way of exemplifying it, so how does this actually make sense, is by looking at spectral probes. So for example, you can ask now, what is the probability distribution of spacings of energy levels in this system? And the way to probe it is, for example, to ask how many levels do I find on average that are a separation S apart. So S is the energy difference in some convenient units, in fact, in units of delta, which I introduced earlier. And what you find with a quantum chaotic system is that if you do this and you make the resolution of energy finer and finer, you find that this actually follows a curve that can be calculated using random matrix theory. So the real system has a two-level correlation function that looks like it had been sampled from a certain random matrix integral. And for example, a system that is not chaotic, that will be integrable, just to give you that distinction, would follow this curve here, which is like a Poisson distribution, which differs a lot here around the origin. Okay, so one way that this manifests and has manifested also in the literature on black holes is by essentially the Fourier transform into real time of this two-level correlation function. And that's this famous spectral form factor, which also generically at late times starts matching the predictions of random matrix theory. This was, as I said, generically matched to wormhole contributions at late times. So that's why I'm saying here, chaotic Hamiltonians show RMT statistics. This has an imprint as universal wormhole type contributions. But the point that actually the takeaway point from this slide I want to convey is that we basically define a quantum chaotic system to be such that its energy levels follow random matrix statistics. Very good. So now in gravity, this is something that many of you might also be familiar with. You actually get the same kind of matrix integrals, but from what a priori seems to be a completely different point of view. So for example, going back to the 1980s, actually people have looked at the idea of constructing a sum over topologies and an integral over metrics in 2D gravity. For example, if I look at universes that have one boundary, just let's say we focus on that. Of course, that's not a requirement to make this work. That's what I visualized here. You can write some expansion in topology, which in 2D is just an expansion in genus with some coupling constant. And the trick to generate these is by saying that if you look very closely at one of these universes, you can actually find a way of discretizing the space-time by doing a random triangularization of the surface. And what was recognized, as I said already in the 80s and also the 90s, there was a lot of activities, is that you can actually generate such random triangularization by using matrix integrals. And the way that it works is that that Feynman diagrams of these matrix models, so these would be here now the double line Toft type expansion of these Feynman diagrams. you can associate to these Feynman graphs a dual graph, which gives you exactly the random triangularization of a manifold. And you basically use that matrix integral now as a combinatorial tool to generate different random triangularizations. And what can be done is that you go, you take a continuum limit of these triangularizations, which in this context is called a double scaling limit. And that is a very nice way of constructing the sum over two-dimensional metrics and topologies. Now, as I said, that has a long history, but in recent years, this was reincarnated in a different context, namely in a paper by Sadchenko and Stanford, who actually pointed out that if you think about a two-dimensional asymptotically ADS anti-de Sitter space example of this, in particular in the context of JT gravity, you can make the same story work, but now the matrix that actually generates this triangularization is no longer just a combinatorial tool, but it should in fact be understood as the Hamiltonian of the boundary theory in the ADS-CFT sense. So this is now one of these guys. It's a chaotic Hamiltonian, which is described in terms of random matrix theory because of this, but it also works in much the same way as in the 80s and 90s as a way to construct a continuum version of the 2D gravity fast integral. And so, for example, in this paper, we made very explicit that the potential V from which you actually sample the matrix, this potential can actually be seen as an ergodic phase of a chaotic boundary CFT. Yes.
Oh, maybe you're going to explain that, what an ergodic phase means.
Well, again, I just mean that. Well, okay, yeah. Let me describe it. There was another question.
Yeah, you mentioned that distribution of level spacings is two level correlation and level spacing. Are those two different things that are independent of each other? Or
Sorry, what do you mean actually?
So you have this graph of two
Here.
level correlation, yes. But you also mentioned distribution of levels, energy spacings.
Good.
Are those unrelated or not?
So if I understand your question correctly, they're not the same, but let me just say what's not the same. So the two-level correlation that I compared to Wigner and Dyson, I actually make sure that the two levels that I count are neighboring levels. So they're really gaps between levels, averaged over the whole system. Another question that I can ask is actually what is the correlation between levels without the condition that there is no level in between. And actually, I did this on purpose, and now I need to apologize. When I said this is essentially a Fourier transform, I lied in that sense, because this thing is actually the Fourier transform of the two-level correlation, of the level correlation without demanding that they are neighboring levels. Whereas this, you demand that the levels are neighbors. I didn't want to go into this detail because it wasn't important for what I'm conveying here. But in that sense, there are different notions. But moreover, I can also now ask what is the statistics of all levels? I can also ask what is the three-point function of levels? And I can again make different measures. I can say just one at energy E1, one at energy 2, one at energy 3, without saying that there is no or some levels between them. Or, so it depends a little bit on what you're asking. But the simplest one would just be the statement now that for a quantum chaotic system, the statistics of all level correlations will be sampled from a random matrix Hamiltonian with the appropriate potential.
Yep.
So that's why people talk about level statistics. That's probably the better way of saying it.
Can you say more about, excuse me, can you say more about what properties of a wormhole in particular are being diagnosed using the spectral form factor?
Say one more time your question, please.
You say there's some wormhole-like properties that you can deduce. Which properties are you?
Good. So actually, the simplest thing I can say is that the two energy correlation function, but not the one where I say that they are neighboring levels, that has a universal contribution which leads to a linear behavior of the spectral form factor. That linear behavior can be associated exactly with a contribution of two boundary geometries, which are solutions Euclidean wormholes, okay, which have, let's say, fixed boundary size on either side as boundary conditions. Okay, so then with that in mind, now this straight. Oh, sorry, you can't see when I point, right? Sorry, you're you're on Zoom. Can you see this cursor?
No, but it's fine because I have a video of you standing next to the screen as well.
Oh, very good, very good. So so then there is also this flat face here, which is called the plateau phase, and this, for example, can be identified with a condensate of solutions of this type. It's actually a non-perturbative effect, but it can be associated to a condensate of these two boundary wormholes. And in the same sense, for example, if you looked at 3-level correlations or 4-level correlations with like 3 boundary geometries or 4 boundary geometries. Yeah, so in that sense. I don't know if that answered your question.
I think that's enough. Thank you. I think that's close enough to cover my confusion.
So now something that is more recent is that there is also now mounting evidence that a similar story is also true in 3 dimensions, where we're trying to think about 3-dimensional pure gravity. And we proposed in this model a certain random tensor theory, which also follows from the consistency conditions of what a 2-dimensional chaotic CFT is. And this random tensor theory, for example, contains a diagrammatic expansion, which looks very much as if you were using tetrahedra and certain other vertices to glue together 3D discrete universes. So the diagrams of the tensor theory look like discrete triangularizations of 3D universes. And in increasing level of our understanding, I'm going in shades of gray, we want to also show that you can find some sort of continuum gravity path linker, which also in this case emerges from a double scaling limit of these triangulations. And I showed you here though, and I will be more concrete later, that this is an actual, the actual diagrammatic expansion follows from a potential. For example, the quartic vertex is given by, these are some special functions. This is not so important, but this would be, for example, the Virasoro, the 6J symbol of Virasoro, which gives you the weight for each of these vertices, for example. And again, the potential V can be constructed as an ergodic phase. And in this concept, I think I will, this context, I will reply to your question. Okay, good. So now, but what I do want to tell you about today also is like the reason why such a tensor theory should be actually correct. And so today I want to talk about a more recent paper with my former graduate student Pietro Pelliconi. He has now graduated, and Herman Belindres. So I'm going to give you an idea of why we should be thinking in a 2D chaotic CFT as something that basically averages over certain part of the CFT data. So, however, this is going to go in a slightly different direction also. Maybe if you still have questions here, we can take them now, or of course at the end. Yeah.
So when here in 3 dimensions, you're summing over topologies, are you considering only handle bodies or?
So so I will just give you the honest answer. This, I don't know yet what the answer is, because of course, making technical sense of a sum over 3D topologies is not under control.
What about metrics though? What about metrics? What kind of metrics do you sum over?
Well, here, so what has been tested so far is that you can match, for example, if you say, what are the on-shell solutions? You can try and compute what are their actions by using this tensor model. And for hyperbolic 3 manifolds, they match the calculations, using this approach to 3D gravity that people call Virasoro TQFT. So these metrics, you match their on-shell actions using this tensor theory. Okay, what we don't yet know, for example, is can we match things like these two boundary torus wormholes?
But should I interpret this as Virasoro TQFT then? Or not?
You should think of it as on-shell to be Virasoro TQFT. But this theory also contains off-shell solutions, which you would not be able to capture using that.
What is an off-shell solution? What is it?
Solution that's not, for example, a hyperbolic three manifold. So one example that I just mentioned would be this two torus boundary wormhole, for example, of Kotler and Jensen. These would be actually solutions that are equivalent, well, that are like this double trumpet solution in JT, which are also off-shell.
Okay, there's nothing like that in the Virasoro TQFT with two boundaries.
I mean, they wrote down an answer for it, but they also wrote in their paper that, strictly speaking, the rules that they use it to calculate are being extrapolated. So now I would say that the Virasoro TQFT can only give you answers for hyperbolic three manifolds, and this is not a hyperbolic three manifold. In that sense, it's off-shell. But you might be referring to a particular part of that paper. They do write out an answer. Okay. Good. Other questions? All right. So I want to remind you of something very simple that you all know extremely well. That's the example of a mesoscopic particle which undergoes Brownian motion. So stealing this animation from Wikipedia, what we know what happens here is that there is some probe or some observer, some set of things that we can observe, which satisfy laws which look almost like the laws of, let's say, hydrodynamics, but you get fluctuating contributions on top. So the most favorite example is, for example, the Brownian motion of a mesoscopic particle suspended in a fluid, which famously gives you a mean squared displacement that's proportional to time, or sorry, mean squared displacement that's proportional to the square root of time, which is the square root of this, with a diffusion constant that satisfies some fluctuation dissipation relation. But we know in this case that microscopically this particle undergoes myriads of molecular collisions. And that means that there is actually a description of this process, which is neither macroscopic nor microscopic, but it's somewhere in between, namely mesoscopic, where you say that I can actually take into account the UV degrees of freedom in some sense statistically on average, and I can think of the particle's position now as a stochastic process, where basically I now have an expectation with respect to the stochastic process, and it gives me a behavior where, for example, the velocity field of the particle is viscously damped, so the velocity of this particle goes to zero at large times, but I can actually ask about the correlation of the velocity field at two different times, and I find that there is actually a non-zero fluctuation, which, for example, if I take the times to be the same, so I look at the autocorrelation, then I get an irreducible contribution which remains there. So even though the motion of the velocity, the one-point function of the velocity field seems to go to zero, the fluctuations do not. And the point that I'm making is that this is a description of the particle, which takes into account the UV degrees of freedom, but it takes them into account in a way that is statistical, that is also not exact, but that is still statistical. And so if I look at the mesoscopic phenomenology of this particle, I actually do have some remnants of the true UV, which is here the underlying molecular motion, which is visible in the fluctuation contribution to the particle's position or other observables.
Just to make sure I understand the way you're using mesoscopic, what would you have said is the macroscopic description of this?
Like hydrodynamics, for example.
Hydrodynamics.
Yeah. So, I would like to propose that within within what I'm talking about today, there can actually be an analogous behavior of the gravitational correlation functions. So we can actually use sort of semi-classical probes to get insight about quantum fluctuations. And we might perhaps see that as the reason for this sort of unreasonable effectiveness of semi-classical path integrals, in the sense that the semi-classical path integral actually seems to be sensitive to these UV fluctuations, even though naively we might think it shouldn't be. And we will find a similar behavior, which can be really made very analogous to this boundary motion example. So for this,
sorry, can you go back in this?
Yeah.
So in this gravitational discussion, so this is what you expect. You're trying to make an analogy with the results of the gravitational path integral.
We actually will get this from a calculation in gravity.
But
and to make sense of this, I'm trying to propose that the level of description that corresponds to, well, I will define the probes that we use, is actually one that's effectively mesoscopic. Meaning that, the question was always, why do we actually know, for example, something about the statistics of individual energy levels just by looking at the semi-classical path integral? And what I'm saying is that the semi-classical path integral actually seems to be capturing precisely the fluctuations in the sense of a stochastic process. So it's not truly the UV here, but it has still imprints of the UV in the same sense that the Brownian particle does.
And I have kind of the same question in the gravitational case. What would you have said is the macroscopic?
Well, I would have again said the macroscopic scale is just classical gravity.
Classical.
Good. So for this now, okay. I put this slide in again because I realize that not everyone will have heard about ADS-CFT. So I'm going to study this question within ADS-CFT, this duality, which tells us that we can think about ADS-type physics, so ADS-type gravitational physics, by instead thinking about a theory that lives on the boundary, which is a CFT. So here ADS is this Poincare disk. It's ADS2, but I'm thinking about it generally to visualize ADS in d+1 dimensions. Its boundary is this circle here. This holographic gravity, if you want, is a more precise version of the fact that I said at the beginning, that the black hole entropy is actually proportional to the boundary of the black hole and not its volume. So the number of degrees of freedom scale with the boundary, and the ADS-CFT correspondence realizes quantitatively this idea that I should be able to describe the physics of a given bulk region of space-time by instead thinking of a theory that operates on degrees of freedom that are extensive with the boundary. And so in this context, we're thus faced with the task of constructing some mesoscopic description of chaotic boundary CFTs. Okay, so for example, how could I probe such chaotic boundary CFTs? Well, one way is to shake the system and see what comes back. And that means that I'm actually probing operator correlation functions of the boundary theory. So for example, a 2-point function with 2 operators inserted on the boundary. Now, let's see, for example, if we can get some mesoscopic physics out of these boundary correlation functions. So let's ask, for example, about the 2-point function of a light operator O in ADS3 CFT2. So there I can visualize these things, these diagrams. So because we want a thermal correlation function, I'm giving boundary conditions that the boundary is going to be a torus. And I'm asking about the calculation of the 2-point correlation function. And so now, if I do the gravitational calculation, which was done by many people before, for example, by Maldacena, what I find is that in the leading semi-classical limit, which here is large C for the CFT, large central charge, large local number of degrees of freedom, I find a correlation function which decays exponentially with a characteristic exponent that corresponds to the conformal dimension of this operator delta, and is also sensitive to the temperature. So this shows this exponential decay at large times, and I will also make this a comparison quantitatively in a second, but think of this as being the exponential decay of the Brownian particle, which actually is not sensitive to the fluctuations of the actual behavior of the Brownian particle. But now, what you can do is you can actually say, hold on, I can actually try and ask the question about this variance. And the calculation that you should be doing about the variance, the fluctuation contribution, so I'm writing this as like g beta of t, g beta of s as evaluated in gravity. Because of course, if I just write g beta of t, g beta of s, you say that's just the product of what I had before. But in fact, if I feed this kind of quantity into the semi-classical limit of this holographic correspondence, I'm actually instructed to do the following computation. I'm instructed to do the computation where now I have two boundaries. Each boundary will be one of these tori with the thermal boundary condition. And I should ask what are the bulk spacetimes that actually have the boundaries that I'm drawing here. So two operator insertions and torus topology. And turns out that there are several contributions. In particular, there are connected contributions where I basically think of these operators as Wilson lines that go through the bulk, where I have two different contractions. And well, we redid this computation. We relied heavily on the formalism that was worked out by these people in their paper, Treating Gravity as a Random Ensemble. And we find the following answer, which again has this form that I have something that at large t and s will go like e to the exponent t plus s, and something that will go like e to the exponent t minus s. So exactly the same form as we have. So for large times, you can actually extract these gammas. Gammas will just be some function, of the various parameters beta and delta that you see here. But what you find is precisely that the expectation value with respect to what I think of as the stochastic process of the 1-point function of the light observer experiences an exponential decay. And by the way, this of course I could have called this G0 because it's the initial value of the correlator, but I didn't want to call it G0 because then I would have thought this is the zero temperature correlator. That's why I chose V0. This is not being lazy and copy pasting this Brownian process. But you do find, as I said, an expectation of the 2-point function, where if you look at the autocorrelation, t is equal to s, again, you have this irreducible fluctuation component that remains. And of course, you could go on and you could ask about multi-boundary contributions. So, which would be non-zero and which are in principle calculable. So, what this means is that the interpretation that I will now from the CFT perspective also explain is that you can actually calculate the semi-classical gravity expectation answer, and it decays exponentially and is a smooth function. And you might say that's all there is, but in fact, the semi-classical path interval contains also these fluctuation contributions, which I can tell you about the fluctuation. And these encode the true UV fluctuations of the theory, but they are encoded in semi-classical geometry. And in that sense, I want to think of the semi-classics as being some mesoscopic description. And I think I can put some more meat on it by talking about the boundary geometry, so I want to take 5 minutes to do that, if I may. So let me just actually say that if you ask the literature on mesoscopic processes, if I want to not discuss some sort of velocity field or simple quantum mechanics, but I want to think about just correlation functions in a quantum field theory, what are necessary criteria to have some kind of mesoscopic description? Well, you find that you want to have scale separation, which for us will be the large gap of the holographic CFT2. You want to have a thermodynamic limit, which is the large C limit of this holographic CFT. And moreover, what you want to do is you want to also make sure that the spectral width itself, so here the spectral width is the expectation of the fluctuation of the energy around some microeconomical energy also scales with the thermodynamic limit. And this is the case in holographic CFT. So they actually do satisfy the textbook criteria for a mesoscopic disk. But let's see this in action. So let's focus again on this correlation function of light operators, and I can think of it now as the correlation function with respect to one of these large gap, large C holographic, irrational holographic CFT. So now what I can do is I can expand this, of course, in any channel I want, but let us focus on the OPE channel. This is interesting because what you get is you get two types of contributions. You get a contribution, so these are torus conformal blocks, these Fs. This is the block in the OPE channel, and there is also something in the necklace channel, which we write about in our paper, but which I didn't include in this talk. But in the OPE channel, what you have is basically a contribution where the operators fuse into the identity. So this is this FOP of 1, F bar OP of 1. And then you have contributions where you have OPE coefficients between your operators and heavy operators above the gap of your CFT. And so the point is that if we can even do it, we calculate this part here, we match the semiclassical gravitational contribution, the decaying correlator. And I want to think of this as being the physics that is sort of seen by this mesoscopic observer, whereas this is the true microphysics, and this is the UV microphysics. And so now the tool that I will use is I will actually use the distribution of OPE coefficients from this tensor model to average over these fluctuations. Okay? Now, for this, I'm going back to this ensemble for random 2D CFTs. And the way that we constructed it, I'm happy, by the way, to go into more details about this either afterward or in person. I realize that I'm throwing this at you now. There really is quite a bit behind this work, but you know, I couldn't give 2 talks, I guess. So we use our CFT ensemble for 2D CFT, which we think gives this 3D tensor model for 3D gravity. And so the way that we think about this is that we construct a joint statistical model for the data of 2D CFT, where we have a set of OPE coefficients. In particular, we only include the heavy data in this set of what we will call randomized OPE coefficients and dimensions, and also the heavy OPE coefficients, which will be random tensors. Now, of course, this data will not give you a good CFT unless you impose the crossing constraints. And what we do is, this is the definition of our ensemble. We do not actually say that these bootstrap constraints are exactly satisfied. We write down the max entropy ensemble probability distribution of these quantities such that the crossing equations are actually solved at the level of expectation values with respect to the matrix. And this works and actually gives you a random matrix tensor integral. So this is what I would have called our tensor theory. And in particular, it comes with this quartic vertex, which looks like the random triangularization of 3 manifolds. But more relevantly for our talk, it gives you a statistical distribution with which you can do contractions of your tensors. And so if we do that, if we do the contractions of our tensors here, those are the ones that are random. There's nothing random here because the OPE coefficient that fused to the identity, I can normalize to 1. And so if I use this tensor model, I wouldn't, I guess, be giving the talk if that weren't the answer. You basically match that with respect to this ensemble, you get the correct 1-point function, and you also get the correct fluctuation. I would also expect that, you know, if you calculate higher moments with multi-boundary geometries, you also get agreements, but we have not been able to do these calculations because they rapidly get very unwieldy. So let me conclude here. So basically, as I was saying, I think that this inclusion of the multi-boundary geometries in the semi-classical path integral, we can think of this as describing some kind of intermediate physics in between having like the full description of the UV which should be some specific CFT that is chaotic, and the low energy sector, which gives you classical gravity. And in this intermediate regime, I have some mesoscopic description of the system, which actually looks like a stochastic process, which shares a lot in common with Brownian motion, except, for example, one difference to Brownian motion is that there are arbitrarily many higher moments. They're not just Gaussian moments. So in that sense, you can think of this semi-classical participant as giving you statistical physics of the true chaotic microstates. But surprisingly, the topologically non-trivial geometries give detailed insight into the microphysics. But again, I emphasize only in this mesoscopic sense. And so, yeah, that's basically what I've been saying this whole time. I have one more slide, which is that we basically presented the stochastic process via its moments or via a microscopic and averaging procedure. I think it would be very interesting and also necessary, to further progress, to actually try and get a description where we really include the UV degrees of freedom and integrate them out in a sense to get really a stochastic theory for the low energy sector. And this is something like in the spirit of, if you're familiar with this, is the Caldera-Leggett model. And that would give you a one-sided effective field theory, which through the stochastic sources implements the effects of what we would have thought of as space-time topology in the calculation, direct calculation of the moments. And via this Caldera-Leggett approach or analogy, there might also be an interesting way of thinking of decoherence, namely of the decoherence due to the UV degrees of freedom on the low energy degrees of freedom that you're actually describing with the semi-classical pattern. So I'll leave you with that, and I'm open to your questions. Thank you. Yeah.
So maybe in one of your last comments, when you said that you want to build a, say, Fokker-Planck equation describing this. So what you have in mind is that you write down a Fokker-Planck equation whose stationary solution is going to have the expectation values realized by the thermodynamical state you wrote down. Is that what you meant?
Yes, but actually, I think it's probably easier to go through the route of the Langevin equation, but I'm not, I'm not committed on that. But yes.
Well, let's see. What does that give you?
What does what give me now? The Planck or the Langevin equation?
No, either. So having this equation which tells you how generate, say, initial condition with time evolve on average.
Well, I mean, one way, one thing that it gives me. So first of all, I'm trying to argue that this gives you an understanding of why you get. You should have a correspondence between the semi-classical gravity pattern goal and some kind of ensemble of things. Here, this ensemble is described by a stochastic process. Now, why am I saying I would like to go to Langevin equation? It's because all I have done so far in the gravity, like mesos in the semi-classical gravity calculation, is I've just followed my nose and I've calculated these correlation functions which somehow encode these fluctuations. Now, of course, if I have such a process, if I have something like this,
I see. You mean you can do direct time evolution to extract these things?
If I have a process like this, I know that there should be a corresponding either Fokker-Planck or Langevin equation, which gives rise to this process, which would be something like an equation directly for the correlation functions with stochastic sources. This would be like a one-sided theory in which I don't talk about like the complicated space-time topology. I just have the usual ABS-CFT, but I have a stochastic ensemble which I can implement to get higher moments of this correlation. And so, yeah, I want to say it's sort of like a Lorentzian version of this Coleman-Weinberg view on wormholes. You have some disorder, you have some noise. And you can either think of it as the Lorentzian evolution with respect to the noise, and you get these moments because now I have a Langevin equation, for example, or you can think of it as being like you have these moments which are encoded in non-trivial topology spacetime manifolds. Yes.
So have you made progress into this direction of getting Langevin equations that correspond to the stochastic progress?
No, I have. Well, I mean, I am working on it. I don't exactly know how it works at this point. I am, let's say it like that. I am working on it.
Okay, there are no more questions. Let's thank Julian.
Ensemble, see anything sense, very, very,